Hi Algebra 1 students. This lesson is on estimating a population mean using a confidence interval. So let's review what a sampling distribution looks like for means. So sample means, we have all these x bars with the distribution of x bars. So the shape is approximately normal, that symmetric and single peaked, if it comes from a normal distribution or n is greater than or equal to 30 from that central limit theorem. The center, mu of x bar, will be the same as mu from our population. Our spread, sigma of the x bars, will be sigma over square root of n. Remember, it shrinks. So we have the conditions. A random condition needs to come from a random sample. It's normal if the sample comes from a normal population, or n is greater than or equal to 30. And it's independent if the sample is independent or we follow that 10% condition. So we have our statistic. In this case, our best guess is that x bar to the true mean plus or minus the critical value, z star, times our standard deviation of the statistic, that's sigma over square root of n that we talked about. We must know the population standard deviation to construct it like this. So most of the time we don't know the population standard deviation. It's very rare because we're using this to guess about the population. So usually we don't know that much about it. The only time we are going to see this where we know something about the standard deviation is this determining sample size. Now, the students have said that these determining sample size questions from both sections come up a lot on the multiple choice section of the AP test, but that's about it. It's not that exciting. Researchers would like to estimate the mean cholesterol level mu of a particular variety of monkey that is often used in laboratory experiments. They would like their estimate to be within 1 milligram per deciliter of the true value mu at a 95% confidence level. A previous study involving this variety of monkey suggests that the standard deviation of cholesterol level is about 5 milligrams per deciliter. Okay, so this is a population standard deviation that we don't typically have. Due to the cost of obtaining monkeys, the researchers would like to minimize the sample size. What is the smallest sample necessary to create a 95% confidence interval within 1 milligram per deciliter? Okay, this is our margin of error. So just like in our last section, we take our margin of error, which is our critical value, times our standard deviation of the sampling distribution. So we have 1 equals, well, if 95% confidence interval, our z star would be 1.96. And we have sigma over square root of n. So we have 5 over square root of n, which we don't know, so we'll just call it n. And then just like in the last section, you could solve this using your algebra skills, but why bother when we have our beautiful calculators that will solve it for us? Menu, algebra, solve, and for the variable x, comma x. 96.04, and we're trying to be conservative, so we round up to 97. So like I said, we rarely know sigma if we do not know mu. Okay, these population values are very rare that we know them. So we will not ever really use a one sample z interval for a population mean because our sampling distribution requires the population standard deviation. So we have a new distribution that we're going to talk about, the t distribution. T distributions are like the standard normal distribution, except we now care a little more about the sample size. It's used to find what's called the degrees of freedom. So degrees of freedom are whatever n is minus 1. I'll talk more about that in class a little bit. For now, just remember it's n minus 1. We can find t star, the critical value, on the calculator. So suppose you want to construct a 95% confidence interval for the mean mu of a normal population based on an SRS of size n equals 12. What critical value t should you use? So just like we did this before, I'm going to draw my distribution. So 95%, which means there's 5% in both tails, which means there's 0.025 in each tail. So when we're looking for our t star, and we could find this negative t star if we wanted, we'll need to know degrees of freedom. So remember, degrees of freedom are n minus 1. So degrees of freedom, n is 12, so degrees of freedom 11. So we go to menu, statistics, distributions, and then instead of inverse norm, we're going to use inverse t. So 2.2. Now, little thing that my students liked from last year, they use this area of 0.025, realizing that the negative value would be the same as the positive value because they didn't want to do as much math and add that 0.95 and 0.025. That's perfectly fine. So t star is 2.2. Notice that it's a little bit larger. It's not that far off from a z that we would expect. Remember, the z is 1.96. And now let's see, what if n equals 25? So the only thing that would be different is our degrees of freedom would be 24. So would you expect t to be bigger or smaller? Well, t is going to be smaller, this t star, because as n gets bigger and bigger, this t distribution is closer and closer to a normal distribution. .06. So we're getting closer. Now we have standard error of the sample mean. So we don't know sigma. So our best guess for sigma is the standard deviation from the sample. So this is not a bad guess, and this is the average distance the sample means are from the true mean, right? So it's just the standard deviation, but it's the standard deviation of the sample, not the population, because we rarely know that. So putting it all together, we have x bar plus or minus t star times s of x over square root of n. We still have our conditions, and let's do an example. Environmentalists, government officials, and vehicle manufacturers are all interested in studying the auto exhaust emissions produced by motor vehicles. The major pollutants in auto exhausts from gasoline engines are hydrocarbons, carbon monoxide, and nitrogen oxides, NOx. Researchers collected data on the NOx levels in grams per mile for a random sample of 40 light-duty engines of the same type. The mean NOx reading was 1.2675, so this was from our sample, so it's an x bar. And the standard deviation was 0.3332. So this is also from the sample S of x. Construct and interpret a 95% confidence interval for the mean amount of NOx omitted by light-duty engines of this type. So the procedure in context. This is a one sample T confidence interval for the mean NOx. Our conditions, well, we were told it was a random sample, so it meets that condition. Normal, n is greater than or equal to 30, right? It's 40. So we know by the central limit theorem that the sampling distribution is approximately normal. And independent, we don't know if those are independent, but we can assume that 40 is less than 10% of all readings. Horrible handwriting, but you know what I meant because you were listening. And our calculations, so we have our x bar, 1.2675, plus or minus our t star. Our t star was 95%, and the degrees of freedom is 39 because we had 40, n minus 1. So 2.02269 times our standard deviation 0.3332 over square root of n, so square root of 40. Put all this in the calculator. And there's our confidence interval, 1.16 to 1.37. And we interpret this. I don't have enough space, so I'm just going to read it for this one. We'll do more in class. We are 95% confident that the interval from 1.16 to 1.37 captures the true mean NOx emission level. The EPA sets a limit of 1 gram per mile for NOx emissions. Are you convinced that this type of engine has a mean NOx level of 1 or less? Use your interval to support your answer. Well, is 1 in our interval? No, it's not. So I'm not convinced. No, because 1 is not in my confidence interval. So here's some notes. If we have a sample size of less than 15, use T procedures if the data appear close to normal, roughly symmetric, and single peak, no outliers. If the data is clearly skewed or outliers are present, you cannot use this T, right? Typically, we look at this if samples are greater than or equal to 30, the central limit theorem comes into play, and it's fine. For a sample size at least 15, we can use this if there's no outliers or strong skewness, and from greater than 30, central limit theorem comes into play and we're fine. No matter what, the sampling distribution is going to be approximately normal. Okay, so very small samples, so from 0 to 15, we're looking for approximately normal sample. From 15 to 29, we're looking for no outliers or strong skewness. We're still going to be okay. And then greater than or equal to 30, it's fine. A manufacturer of high-resolution video terminals must control the tension on the mesh of fine wires that lie behind the surface of the viewing screen. Too much tension will tear the mesh, and too little will allow wrinkles. The tension is measured by an electrical device with output readings in millivolts. Some variation is inherent in the production process. Here are the tension readings from a random sample of 20 screens from a single day's production. Okay, so construct and interpret a 90% confidence interval for the mean tension mu of all the screens produced on this day. So the procedure in context is a one sample T confidence interval for the mean tension reading. Conditions. Is this a random sample? Yes, it says it's a random sample. Normal, we have 20, so we need to check from what we have up above, we need to see that it's no major outliers or strong skewness, and then the sampling distribution will be approximately normal. So let's make a graph. So our dot plot doesn't tell us very much, so I'm going to change this to a histogram. So I don't see any major skewness or outliers. I'm still not convinced. Let's try a box plot. Well, definitely no major skewness or outliers. It looks like a box plot is the best option for us to see all of that. So if we're going to do that and use this, we should probably draw a sketch somewhere on here. I'm not going to do that right now because we don't have that much time, but no major skewness or outliers. So the sampling distribution will be approximately normal. And independence, these 20 tension readings need to be less than all tension readings that day, and we can make that assumption. Okay, now we need to do our calculations. So we need our x bar plus or minus our t star for 90 times s of x over square root of 20. Now, I can do all of that. I can look all that stuff up with one variable stats. Right, there's my x bar 306.32, and there's my s of x. Do not use the sigma because it's not sigma this time. But I'm not going to do that because I'm going to use my calculator for the whole thing and show you how to do that right now. So we go to Menu, Statistics, Confidence Intervals, and this is a t interval. Now we have data this time. We can sometimes are given statistics. Like in the first example, we were given the x bar and the s of x. Those are the statistics. But in this one, we were given all 20 pieces of data, so that's what we're going to use. And that list is tension. The confidence level is 0.90. And there we go. 0.292, 0.32, and 320.32. There's the degrees of freedom, 19. There's our x bar and s of x too. We should write down all of this stuff. Okay, again, I'm saving time. I'm telling you what to do. Write down all of these things for the AP Stats test. If it's important enough for your calculator to say it, it's important enough for the graders of the AP test to know it as well. And again, our interpretation, we are 90% confident that the interval from 292 to 320 captures the true mean tension reading good enough for the day.